Okay. So the first slide as 00 is given across with the introduction part. Okay, we will discuss about what are the various outcomes. So as in the syllabus I have shared in the Google Classroom. Right? I have shared the syllabus as well as lesson plan in the Google Classroom. Okay. So what are the various prerequisites? And these prerequisites actually are required. Okay. If these are essential prerequisites. You should have a thorough knowledge of network theory, KVL, KCL, the basics of network theory, electrical machines, because we are going to study about power system stability, then transmission distribution, okay, and finally circuit protection. So these four you have studied in, I think, last 4 semesters. You have studied all this. Okay, so you are moving up to the power system operational control. So these are 5 basic parts. When we say PSOC, in masters they study this as power system analysis. Okay, the first part is related to network theory, which is load flow and power flow studies. So how power flows in the whole power system grid. Okay, so that will be our topic for the first module. Okay. Second module is economic operation of the power systems. Now we have a certain demand in the power system, and we have to meet the demand. So how it can be made with least cost. Okay. But this is mostly related to the thermal generation, right? The economic dispatch as it was developed was for thermal generation, because thermal generators involved coal, and we have to minimize the consumption of the coal. Later emission was introduced, minimize coal consumption as well as minimize emissions. Then nowadays then came hydro. So how to coordinate hydro and thermal so that the cost and emission are minimized. Then now current research is related to wind, solar, integrating all these things inside in the power system dispatch. Okay, data point dispatch. The third one is the most important aspect, power system stability. Okay, this grid. Okay, so this grid is national grid. So you know that now our whole country is interconnected. So how this grid is stable under various disturbances. Like small scale disturbances like load changes. Every day load changes. So how the grid will meet that without being unstable. What is the meaning of grid being unstable? That means some generators go out of the grid, eventually it's a blackout. So one generator goes, results in more stress on other remaining generators. One by one, each generator goes. It happens. Sometimes, occasionally it happens. But now the grids are very robust. So it doesn't happen frequently, but it happens. Okay. And the source of this stability is actually synchronous generators. Okay. Which are now being replaced by wind generators and PV. So the whole power system needs to be redesigned. So who will provide for the stability? The big guy, okay, which is the synchronous generator, was keeping the whole system stable. But that inertia, who will provide? So that is the question. So if you only put microgrids, then how the system will be stable? Okay. So when you have a bridge, there are some strong supports. Now if you remove that support, the small supports cannot hold that bridge together. Right? It's the same. Fault analysis. So faults happen. 90%, about 70% faults are single line to ground faults. Okay. So whenever faults happens, it is actually a large disturbance. So normal stability, steady state stability means how the system handles small disturbances. Fault means a large disturbance. So how the system will withstand very large disturbance like a fault and again come back only. Okay. And finally, the last part is also steady state problem, which relates to how to maintain frequency and voltage in the system. That is what automatic generation problem. So this part, this power flow studies, economic dispatch and automatic generation control, these are basically steady state problems. These are basically steady state problems. Whereas these two are mostly, you can say, dynamic. Okay, dynamic means when time is increasing. So in these three cases, it's actually a snapshot of the power system. Load flow means, suppose you now on the top with a drone to take a picture of the traffic. So now you know how many cars are there, how many cars are flowing over a particular flyover, but that's a snapshot. Okay, but in power system also, load flow means at this instant what line is taking how much, or how much power is flowing in each of the lines, right? So that is known as steady state problem. Okay, what is the voltage and frequency? The last one. This is not exactly steady state because we are also concerned about the frequency stability. Okay, but this is related to whenever a fault happens for next few cycles, how the system is going to behave. Okay, can it again come back to its original position? So that is known as dynamic problem. So here we concern about T plus delta T and so on. Whereas in case of steady state, it is only a single time snapshot of the system. Now, so this is what you have read to reach here, to reach PSOC. Now after reading PSOC, what further subjects you are going to read? Now remember that as I told, PSOC is basics of electrical, very basic. So everything else that is discussed about smart power grid, cyber physical systems, everything is built on PSOC concepts. So one related subject is high voltage. This is not exactly PSOC, but it's related to high voltage, how system behaves under high voltages. Then facts. Facts is how to make transmission system more efficient. Okay, in terms of reactive power consumption, real power consumption. Then power quality. This is more important when you integrate PV, wind into the system. Then renewable energy and electric vehicles. So when electric vehicles charge, nowadays there is a concept that if you have so many electric vehicles and they have spare energy, so when there is a power cut, so you can supply power from the EV itself. So there is theoretical possibility, but I think in some countries this happens. Okay. And finally, so as in the trade, smart power grid. So what is smart power grid? Inclusion of AI/ML, IoT, Internet of Things, cloud computing, cyber security, blockchain, all these things when you work in the power system, it becomes smart power grid. Okay, everything is automated. So what you are going to learn after the end of the course, this is even semester. So by February 20, we are going to complete 3 modules. Next, within March and April, first 2 weeks, next 2 modules. So it will be very fast. Okay. So within this time, you are going to learn how to compute. Upon completion, the students will demonstrate the ability to compute load flow solution by using different techniques. Determine the economic distribution between generating buses, incorporating transmission process. Assess the stability of the power system. Compute the state of the power system following different types of faults. Describe automatic generation control schemes and methods to analyze active and reactive power control using simulation tools. And all these are there in your power system lab 2. So there are 9 experiments in power system lab 2, out of which there are 2 experiments which are only using software tools for all this purpose. You will use various programs for load flow, stability analysis, fault analysis, AGC. So all these are there in the power system lab 2. The basic one. These are the starting one. After that, if somebody wants to do research in power system, they can write their own. Okay. Okay. So next, the related concept which is beyond PSOC is cyber physical system. So what is actually a cyber physical system? Yeah, anyone who knows? It's a physical system, also cyber. Okay, as a power. You have communication also, you have physical transfer of energy also. Okay, so the power and energy system can be described as a cyber physical system where a network of heterogeneous energy suppliers and end users from the physical layer, the sensors, communication networks, supervisory control, data acquisition control systems from the cyber layer. We have got the hardware, the transmission lines. Okay, so if you pass through the country in road, you are now very good. So you will find out various transmission lines. Okay, you can see the physical infrastructure. It has become more advanced. So we are still behind some of the neighbors, but still the transmission systems have become very advanced. So this is the hardware that is needed for transferring the power. But beyond that, all the control, all the programming, all the dispatch is happening through software. And there is communication between various hubs of the power system. In EPC they study about communication system. So they have various layers, right? There are some layers in communication system. You know that? There are some 7 layers. Okay, open system interconnection layers. Okay. Similarly, here also there are some communication algorithms which are used. That's why it's a cyber physical system. For example, most widely used is SCADA system, which is known as supervisory control and data acquisition system, which is used invariably every substation. Okay. Recently, increasing deployment of smart metering infrastructure for modern. Nowadays, you have got 2-way meters. Okay. Nowadays, nobody comes to read your meter. In many of the cities, no person comes to read the meter. So automatically, the is built somewhere. There is a SIM inside it. It communicates, and you get the bill directly in your mobile. Okay. It is a many cities. Okay. The other part, the first part is the cyber physical system. This is the big one. The other part is microgrids, small scale power systems in kilowatts. Micro, why it is micro? Our normal power system is in megawatts, right? Whereas microgrids is 10 to the minus 6. It is in watts and kilowatts. So that's why it is microgrid. So a typical university can become a microgrid with solar. Okay. Many of the African countries I have heard, there was a news article that there is a PV based microgrid which is making so much development in a particular region where there is no grid power available. Okay, so microgrid can be made using solar and all the locally available small hydro, locally available power systems. Okay, but microgrid poses many challenges. Like the quality of the power that is used in microgrid, if that is inserted into the main grid, might create power issues. Okay, so microgrids are limited electric networks designed to provide a small number of users with an efficient and high quality energy supply. They are employed to maximize the contribution of the integrated distributed generator. Distributed generator, currently our system is centrally controlled. We have got big power plants which are supplying power from some remote location to the consumer system. But microgrid are on site. There itself we have got generators, small generators. So that's why they are known as distributed generators. Okay. Regarding numerous advantages of the microgrid, we have certain challenges due to real-time operation like control protection, irregular random without energy generation. Okay. Generate can be this one you write. Okay. What is microgrid you write first. This one you write. Okay, this is the definition. So you should write. Generally it can be described as a local cluster of interconnected distributed generators and load, the operation of which can be managed without connecting to a larger grid system. Okay. So without connecting to a larger grid system, we can operate the microgrid. So that is the specialty of a microgrid. Okay. So whenever you are submitting your innovative assignments, okay, you can take any of these futuristic topics: cyber physical systems, microgrids, how to solve the problems of the microgrid, EV charging if included in the microgrids, what problems it will create, power quality issues. So these are some innovative assignments that you can do. Smart power grids. So how cyber threats. Okay. So all these assignments is innovative. Okay. Every microgrid requires an energy management system. So you have an energy management system, and it is built upon sensors. Okay. Sensors everywhere. Okay. Just like I told you, smart meters, they communicate through some SIM. Okay. Okay. So EMS, just like economic dispatch problem, EMS has a multi-objective optimization problem to solve. Okay. So what are the various challenges of the power system? So after studying PSOC, okay, and if you suppose happen to join some PSU or you happen to work in some sector which is working in the power system, so what are the various challenges? Okay. Electric power network efficiency and security deals with fundamental issues of understanding the security, mostly the security, whether the generation will supply demand or not, that's security. Okay. Efficiency how exactly it provides that. Okay, and behavior under disruptive and catastrophic events. So whenever there is a natural disaster or a cyber attack, how the power system is going to handle that. Okay. So another topic. So your assignment can deal with this. There is an urgent need for the development of innovative methods and conceptual frameworks for analysis, planning and operation of complex, efficient and secure power networks. The next generation of high performance, dynamic, adaptive, non-linear networks will be designed and operated with interdisciplinary knowledge, because it is not only electrical engineering, you need communication engineering knowledge, you need computer science engineering knowledge, you need cyber security, okay, and various layers are there. Okay, this must be this one is the most important part. So PSOC you can follow. The PSOC subject is a socio-technical system. Why it's a socio-technical system? It's a very complex technical system. But why it is a socio-technical system? Very popular socio-technical system. What politicians promise? Or what? Pani bijli apa? That is what bijli actually electricity is there. Okay. Electricity tariff is a very hot topic. So electricity is intricately related to our social system, social fabric, right? So how if a person doesn't have electricity, he is least bothered about what is there in the power system, how complex it is, how beautiful it is. He is not bothered. They are not bothered about the complexity of the power system. What eventually they need is 24% electricity. Right? That's why these are socio-technical, very very important systems. In fact, power systems or electrical power systems are our ticket to a sustainable future. So if everything is converted into electric vehicles, if all petrol pumps have electric vehicle charging stations and they have electricity supplied to them, then the emission problem is solved in many ways. The battery issues are there, the emission problem will be solved. So this is one of the way forward. So power system is going to remain one of the major part of the socio-technical fabric. Okay? And you as electrical engineers should be able to explain everyone what is the difference between energy and power. Okay. If someone puts a solar PV on his rooftop, it doesn't mean that he will charge his vehicle from the PV directly. No, it doesn't happen that way. Because the vehicle may need 5 kilowatt power, whereas the solar may only generate 2 kilowatts at a time. But energy wise it can be. For example, during the day, during the previous day when the vehicle was not charging, the solar generated, suppose 2 kilowatt into 5 watts, 10 kilowatt hour of energy. 10 units of energy generated. So that's about 25% of the vehicle charge. Right? So the solar PV system can provide more than the energy needed for charging the vehicle, but it may not provide the exact amount of power. Fine. So for that power, the person will take from the grid. So you as electrical engineer should be in a position to explain this to the person. Many people have the opinion that they don't know electrical engineering. Okay. So they will say that I will charge you every from the solar PV. Why is it not charging? It's not possible. How can a 3 kilowatt system charge a 7 kilowatt charger? Is it possible? That will be 3 kilowatt is the maximum power. Most of the time the solar will generate around 1.5 kilowatt of that because of the annual capacity. So other very futuristic trends are fault tolerant and self-healing networks. Now you have read about self-healing AI systems. You have self-healing networks. Now we have some version of it. Auto-reclosing circuit. Fault occurs, circuit breaker opens the circuit, but after a few seconds it will close it again to check that whether the fault has been removed. Like a tree which has fallen is barred. That's why many times we see the current going and coming back, again going, coming back, it is auto-reclosing circuit breakers. But if the fault is permanent, it is automatically disconnected. Economics, environmental issues are there, so we need to find out various sustainable ways of generating electricity other than coal. So we have various benchmark test systems on which power system tested. That you will introduce in the power system lab also. Okay. So textbooks, I take all the modules from various different textbooks. Okay. So notes will PPT will be sufficient. But if you want to refer, these two are classical textbooks which you might have referred in power generation. But these three books are more than sufficient. LGAD is a classic book on power systems, very fundamental. If you want to understand, if you have time for gate, you need to read this book. Harishadat is a further detailed book, but mostly it is for PG students. Further details. Okay. You want more details. Okay. And this is another classical book. Mostly I will follow all the books. Okay. Some part of it